Hello, I'm Luis Rosales.
I'm Matthew Gomez.
Arlene Cardona.
Christopher Barrios.
And my name is William Portillo, and our project is microgrid sizing for resiliency. Our advisor is Dr. Masood Shahverdi, and our client is Mr. Apter from Southern California, Edison. Next. Okay, so here we have our agenda. Really quickly, I'm gonna go over it. Number one, we're gonna talk about the problem. Then we're gonna go into introduction background. Next, we have project goal, project scope, project organization, schedule, requirements, deliveries, and finally, we're gonna talk about summary. Next. On Wednesday, September 20, 2017, at approximately 6:15 a.m. local time, Hurricane Maria hit the island of Puerto Rico, causing unprecedented damage to the island and the locals. Even after 3 months of rebuilding the grid, 45% of the population did not have power. It's natural disasters like this that make us believe we can do better. We need to manage the burden that natural disasters, wildfire, place on Southern Edison as a utility. Also, we need to maximize the penetration of renewable energy-based generation. Next.
Intro, project background. First, we're going to discuss what resilience is. Resilience is the ability to adapt to changing conditions and to withstand and recover rapidly from disruption. Microgrid. The United States Department of Energy defines a microgrid as a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that act as a single controllable entity with respect to the grid. In this microgrid, there is 3 different operational methods it can function. The first method is considered non-operational. The second method is operational and parallel. In this method, we have the grid delivering power and also our microgrid delivering power to our customers. And the third method, this is the operational and island. In this method, our load and customers are just being sustained by our generation from distributed energy resources. For example, here a few of our distributed energy resources would be a photovoltaic. Also, we have the maximum power point tracking MPPT. This helps out the photovoltaic keep track of its maximum power. We also have the battery storage, wind turbines, and also diesel generators. And just to elaborate more on the distributed energy resources, these are any resources on the distribution system that produce electricity. Project goal.
Project goal. Project goal. Develop a microgrid system that will have the ability to operate independently off the grid in order to sustain the electrical demand in case of major grid failures that may result from natural disasters from our customers. Next. Project scope. We need to determine the upgrades needed for the existing circuit. Also, size the distributed energy resource to sustain customer load for a prolonged outages. Next.
So this is our project organization. So starting off with Michael Thorburn, director, Masood Shahverdi, our advisor, Luis Rosales, our team leader, and our liaison, Abder, and then William Portillo, sizing battery, Christopher Barrios, sizing PV, Arlene, ETAP, relocating generation, and Matthew Gomez, testing battery storage. Next. So this is our schedule for the entire year throughout the project, which describes our different tasks on our left side. And on the right, it shows the completion or how long it took within both semesters. Green describes our fall semester and red describes our spring semester. Next.
All right, so for our requirements, we want to have a functional 13 bus node feeder as a base for the microgrid. And we also want to have to supply with a demand of using a photovoltaic with a battery storage, as well as use the peak load data in order to properly size the generation. With the microgrid system, we must be able to operate in island mode. So meaning it should be able to sustain the load while being by itself standalone. And for performances, we want to have the bus voltages to not deviate more than 2.5% from the nominal value. Conductors must not be overloaded beyond 100% of their maximum current limit. System shall also have a resiliency of 4 hours. Bus frequency shall not deviate by more than 5% of the nominal value. Next. We also have the deliverables. So for our 13 bus test feeder, we want to find like the peak load forecast. With the Simulink models, we want to have the inverter, the PV standalone, the boost converter standalone, the PV with the MPPT, the lookup tables, as well as the ETAP. We want to have to relocate the PV source, the load scaling, and battery storage testing. Next. So for the 13 bus feeder model, we want to operate at 4.16 kilovolts, highly loaded with voltage regulators, transformer, underground and overhead lines, and shunt capacitors. At the bottom left, we have the line diagram of the test feeder. And then at the bottom right, we have our actual grid of the Simulink model for the 13 node test feeder. Next.
So here's the projected load profile. We determined that the system would reach its peak demand on July 7th at about 4 p.m. So what we did was we plotted the projected demand for that day in order to use that to accurately size our PV. So as I mentioned, we noticed that the peak occurred at about 4 p.m. and the peak demand is expected to be approximately 552 kilowatts. So we would need to size accordingly. In order to account for any inaccuracies with this projection model or just any daily, hourly fluctuations, we decided to assume an initial PV sizing of about 650 kilowatts. Just like I said, in case of any inaccuracies, we want to make sure there's enough supply to meet the demand. Next. So here is the initial system that we created in Simulink in order to test our inverter with PV system. If you notice here, this is the complete block diagram. In the middle, you'll see the actual inverter system. We also have the active reactive power control with a current control loop as well as a PWM controller. In the next couple of slides, I'm going to break down these individual blocks one by one and explain a little bit more about what they do. Next. So if you look here, this is the detailed model of the inverter itself. As you'll notice, it's comprised of 6 IGBTs, which function basically as switches. Now, each one of these has an input signal that's coming from the PWM controller. And the other 2 inputs you see on the far left are the DC input. So right now, this represents a simple DC input, but eventually it will be connected with the PV system. In addition, you'll also notice capacitor and inductor on each one of these phases. And what that does is it acts as a low pass filter, filtering out any high frequencies from the switching voltages in order to get a smooth three-phase AC at the output. Next. So here's the active and reactive power controller. As you'll notice, the two block diagrams in the top right corner in green, those are generating our current references. So what this is doing is it's taking our three-phase voltages with respect to neutral, and it's passing it through this DQ transformation. What that does is it transforms our system from three-phaser quantities into two DC quantities, making it much easier to control. So this generates our VD ref and VQ ref, which is essentially our DC reference points for the voltage. Those are then combined with our active power and reactive power reference, and this system will be able to calculate our current reference. These two current references are then passed through this current control loop that you see below. And again, a similar DQ transformation is performed, which takes the three-phase currents and transforms them to the DQ domain. So now we only have two DC values. We then compare those using a summer. We compare those with the ID and IQ current references that we generated. And we have a PID control loop for each one of those branches in order to achieve the desired set point. We then take that back to the ABC domain to generate our three-phase voltage and current references for the PWM controller. Next. So as you can see here, this PWM controller is taking those three-phase current references that we generated, and it's comparing it with, using this comparator function. So it's comparing it to a triangular sawtooth waveform. And basically what happens is it compares our input signal, which is our three-phase currents, and compares it to the amplitude of that sawtooth signal. Whenever the amplitude of the current is greater than the sawtooth signal, it's going to output a high or a 1. So what that means is when it inputs a 1, these outputs are going to go to those IGBT switches that I talked about not too long ago. And if you'll notice, there's also these 3 NOT gates branching off from the main branches. This just ensures that we don't have any two IGBTs on the same leg conducting at the same time. This would essentially cause a short circuit, which we obviously don't want. So if one of the IGBTs on a common leg is conducting, this NOT gate just makes sure that the other one will be switched off. And these PWM signals are what drives the IGBTs and creates the desired output waveforms that we want. Next. So as you see here, we have the unfiltered output voltage across the IGBTs. So it looks like it's starting to resemble a sine wave, but this is not quite what we want. See, this sine wave, this modified square wave, I should say, is comprised of high frequency harmonics in distortion. So obviously we don't want that. This type of distortion would cause great damage to equipment and cause all sorts of power quality issues. So in order to minimize these effects, we would need to include some sort of filtering to get rid of that distortion. Next. So here's our actual output of the inverter after filtering. As I mentioned a little while ago, we can use a combination of an inductor with a capacitor to act as a low pass filter. What this does is it basically traps those high frequencies and prevents them from passing through to the output. And it only passes the low frequency 60 Hertz voltage and current waveforms, which you can see here. And we also were able to measure the output frequency, and it appears to be very close to 60 Hertz, which is what we want. And this is ensuring that our phase lock loop is accurately tracking our frequency reference and locking onto that 60 Hertz frequency that we desire. Next.
Now we have a PV diagram, and PV stands for photovoltaic, and a photovoltaic system is a power system designed to supply a usable usable solar power by means of photovoltaics. This means that a PV system is a combination of components that enable us to harness the power of the sun in our own homes and businesses. In this example, the outputs of the PV factor are solar irradiance, temperature, shadow, and dirt. And how do we calculate current? Well, we have our formula here. I'm not gonna get into details, but if you wanna understand more in depth, you can pause the video right now, and each term, we gave the definition for each term. So right now you could pause it and you could read what each term means. But next. So under Simulink, we took a PV plot. That's the picture on the bottom left on your screen. That's a PV array plot. And it has two inputs and, well, two outputs. And one of the first tasks for our PV array was to look under the mass. And under the mass pretty much is the picture next to it, the one on the bottom right. And here we can observe how the voltage and the current outputs work. And we can also modify a few things. In our case, we didn't have to modify it. We just had to run a couple tests and make sure that it was working properly. Next. Next, we're gonna continue with the PV, but now we're doing a PV standalone. This means that we just ran a small circuit. We put one resistance, and then we checked the voltage of the PV. On the picture on the right, you guys can see that there's a yellow straight line between 343 and 344, and it's close to the 344. But then on the next to the PV, you can see that it says 343.8. So we can see that there is actual voltage coming out from the PV array. So this was a small test that we also did, and this only expressed that our model was working, and the inputs that we use for irradiance, we use 100, and for temperature, we use 25. And that's the inputs that you guys can see next to the PV array plot on the bottom left. Oh, I'm sorry, it's 1000, not 100. I'm sorry, 1000 for the irradiance and 25 for the temperature. Next.
Boost converter diagram. A boost converter is pretty much electronics put together in some sort of way to be able to manipulate power and voltage input and output. So for instance, here we have the boost converter. And in this case, it takes an input voltage and it's going to increase it. It also contains an inductor, a semiconductor switch, a diode, and a capacitor. Okay, so how a boost converter works. Step one, on the top figure on the right side, as you can see, nothing really occurs out of the ordinary. We just have the voltage source and current flowing through the inductor and going through the diode, and the charge of the voltage source gets stored in the capacitor. And step two, as you can see, the switch turns on now. And in this case, we have current diverted into the path of the switch, in this case, IGBT. The output capacitor still stays charged. However, in this particular moment, the inductor is producing a magnetic field, and the inductor actually has a polarity voltage charge. So step three, as you can see on the figure to the right, the IGBT is turned off. In this case, also the system acts the same way as the beginning. However, the inductor generates a large voltage. This is because the inductor's current stopped, and when the inductor generates a large voltage with opposite polarity of the voltage source, the inductor acts as a voltage source, which is in series with the voltage source. When this occurs, the capacitor is charged even with a greater voltage. And this is how we have an output voltage greater than the initial voltage source. So here we're gonna have a representation of our boost converter in a standalone model using Simulink. These formulas provided on the left right here, these are fundamental for the boost converter. As you could tell here, we have the output voltage formula, VL, which is equal to the voltage source in the input side, divided by, multiplied by 1, divided by 1, minus the duty ratio. Also, you can calculate the duty ratio with this formula. Also, we can determine the parameters of our components, such as the capacitor. As you can see here, we have a formula for that. We have current, the output current times the duty ratio, divided by the frequency and the delta voltage output. We also can determine the parameter of inductor. We have to multiply the input voltage times the VL minus the VN, and then we divide the delta current of the inductor times the frequency and the output voltage. This will determine our inductor. As for this example here, for this model provided, these are the parameters we used. As you could tell, for period, we use 2 milliseconds, and for the duty ratio, we use 58.3%. For the inductor, we use 1.45 millihenries, and for the capacitor, we use 3.23 millifarad. And for our load, our resistant, we used 2. And in this case, we had an input voltage of 250 volts. And therefore, based on our output formula, we should have a boost, an output voltage of 599, very close to 600. And as you can see on the next slide, here we have, this is actually our output voltage of the boost converter. As you can see, we have a little bit of transient in the beginning, but it's it happens for a very, very short time. And then it becomes steady. It goes really close to 600, which that's the output voltage that our boost converter calculated. Okay, here we're gonna actually put the PV and the boost converter connected. As you can see here, we have our PV model, and starting from this section, this is the boost converter. And in this model, we have an input voltage of 198 volts. And then we, based on our formula that we showed the last slide, we can determine our output voltage, which is 453, 23 volts. The output voltage of boost converter, as you can tell, it's right where our right where it was calculated. There is a little bit of noise, but then it becomes it steadies out, which it lets us know that our system is doing its job correctly.
Okay, so we talk about the PV array, we talk about the boost converter. Now let's talk about the MPPT. An MPPT are used to increase or maximize the output power in a photovoltaic system. MPPT is an algorithm implemented in the PV inverters to continuously adjust the impedance seen by the solar array to keep the PV system operating at the peak power of the PV panel. The algorithm helps control the voltage to ensure that the system operates at maximum power point on the power voltage curve. And on the left, you guys can see a screenshot of the algorithm that we are using. Again, I'm not gonna get into details, but you guys can see a bunch of if statements, the power formula. You guys can see our inputs, and you guys can see at the end what each term stands for. On the bottom right, we have a visualization of what an MPPT actually does. So on the red line, pretty much does how it would work without an MPPT, and the left curve shows how the same system can work with the MPPT implemented. Next. Now, like I said in the beginning, we talk about the PV array, Luis talked about the boost converter, and I talk a little bit about the MPPT, but this is how it looks put together, everything, all three. And like I said in the beginning, how we ran tests just with the PV alone. And then Luis talked a little bit how we ran tests on just the boost converter alone. And after we got everything together, and that we noticed that the tests that we ran were successful, it was time to put it all together. Next. And now we have our current voltage curves and our power voltage curves. On the top, this is our current voltage, and at the bottom is our power voltage. And each graph has 3 lines. The top curve is irradiance is 1000 and power is 101 kilowatts. The middle curve is irradiance 500 and power is 50 kilowatts. And the bottom curve does irradiance 100 and power 9.5 kilowatts. Next. Now we have a simulation of our system with the MPPT. And if you guys remember, when we first ran the test for the PV array, and when we look at the scope, it was only one straight line. Well, our MPPT is supposed to behave the same way with one straight line. Right here, you can see that it's not one straight line, and you can ask, okay, why is that? Sorry. Let me explain real quick. The only reason this is not one straight line is because we were changing our input, the irradiance. If you guys remember in the beginning, the PV array has 2 inputs, temperature and irradiance. So when we have 600 irradiance, it looks like the first section of the graph is 600. Then we change it to 1000, then it goes up, and then 1000 stays at 1000. Then we change it back to 500, it drops down, change it to 100 irradiance, continues dropping down, and then we change it back to 1000. So we can see that when we put the input, when we change the input also on our scope, the line changes. Next.
So this is a load lookup table that describes for a day of July. So this shows our peak values, which are in yellow for our active power of our load demand, and our blue defines our reactive power of our system. Next.
All right, so with the data table that was provided to both teams from Christopher Serrato, a graduate student, we were able to use it to create a simulation display to find how irradiance and temperature go hand in hand together. GHI stands for global horizontal irradiance. So on the right side, we have a simplified block diagram of the Simulink model. We can insert the hours of the days into the GHI and the temperature to see how much it's giving off in a day. With the PV added onto the GHI, we can also get the PV peak that can be shown its highest power of each hour of the day. Next, on the left side, we have the actual more complicated diagram of the lookup table that we created in the Simulink. We have a couple of gains and dividing aspects to give the PV peak of what if voltage to give us a current. On the right side, we have a display of the entire day of the PV peak showing its power throughout the day for each hour of representing each of the dots of the ramp. Next.
So if you look here, we've replaced the simple DC source with a subsystem as our input to the inverter. This subsystem is the PV with boost converter system that we talked about a little while ago. And as you can see, it has two inputs. It has the irradiance, or GHI, as well as the temperature in degrees Celsius. So now we had a more dynamic way of changing the inputs to this inverter system and seeing how it affects the output. We also have projected GHI and temperature data. So by varying those values, we'd be able to see how the output would change. Next. So here we have a table of the projected output. So earlier we found the projected demand for this July 7th in 2030. So we also were able to calculate our estimated aggregate output of this PV source using the projected temperature and GHI data. So we built several cases for every hour of that day. And by changing the GHI and the temperature inputs to the inverter system, we were able to calculate the total average output power for that particular hour based on these input parameters. Next. So this was a table that we created in order to build our ETAP cases. We decided to use ETAP to run some steady state load flow analysis in order to not only verify the sizing of our PV and battery storage system, but also make sure that there weren't any violations or issues or any upgrades needed to our microgrid system. So for every hour, starting from 12 p.m. till 12 a.m. of July 7th, 2030, we had the projected total demand in kilowatts. And we also broke it down by how much percentage of that total peak demand would be present in each sector of our system. So we broke down the percentages at every hour for residential, commercial, industrial, and other miscellaneous loads in order to build our cases. And then based on each hour, we built a separate case and we updated the loads accordingly, as well as the expected output based on our GHI and temperature data that we have. Next.
All right, so by using the system advisor model, SAMS, we're able to import the yearly load data as well as the GHI data to this program by simulating with a PV and the battery storage. With that being said, we were able to generate an entire year's worth, basically going from month by month of showing us the energy and the peak data, especially giving us annually throughout the year. Next. So after running the simulation of the data, we are able to generate an Excel sheet of various outcomes that gives a wide range of values that can give the best revenue. From looking at the best value to go along with our actual simulation models, we chose for the battery bank size and power to be 600, as well as the desired size of the PV to be 600. This will give us the best net present value of 326,051. Next.
So this is the IEEE 13 bus feeder, which we use as a baseline, which we perform different analysis to determine nominal values and voltages. As we can see that we have different loads, and by analyzing it, we determine nominal values. We're reaching up to 100%. Next. Next. Oh, this is the alert view from our analysis from previous baseline, which describes like what is occurring at different bus lines, transformers, cables, and lines, which our ratings determines our rating and our operation based on different phases, A, B, and C, and our operational percentages. Next.
This is one of the cases. This is case at 5 p.m. When we did this case, the reason why we chose this, it was because this would be considered the worst case, and the fact that our loads would be consuming a lot of kilowatt demand, and our PV generator wouldn't be able to sustain. So this is why we wanted to test this case. However, during this time, when the PV is delivering 105 kilowatts, and our battery source is delivering 364.9 kilowatts, there isn't much problems with our cables or our transformers. The only issue that we did come across during this analysis was on our residential area, which is the top left. We did have low power factor percentages. We had a low voltage. I mean, we had voltage droppage. As you can see here, we have a 59.99 on this load, and then we also have on this load over here 76.11. That is not good for our system. However, our commercial sector, we have a 99.17, which is good. And then we also have a 99.79, which is good because it stays within our 2% our limitation for voltage droppage. Also, for industrial, we everything's looking good. Then here we have our, this is the alert view for this case at 5 p.m. As you can see, we have under voltage situation, and this is, like I mentioned before, this is considered our residential area. And here our transformer does seem to show us a little bit of unbalanced current. Okay, this is also our same case hour, which is at 5 p.m. However, what we wanted to do here is we wanted to scale up our load by 1.5. So the reason we wanted to do this is because we wanted to determine if our system would need an upgrade. We wanted to see if our conductors can hold what our voltage, what our generation sources are delivering to our loads. We also wanted to see if our generation sources can actually sustain the loads for our system. Uh, as you can see for this case, um, our PV is generating 105 kilowatts, and our battery storage is delivering 562 kilowatts, which this is a good sign. This lets us know that if our load becomes gets multiplied by 1.5, we have our system will keep being able to sustain this at least for this hour. And yes. And right here, we do have a few alerts, some violations. As you can see, we still have those under voltages from the residential area and those same current unbalances. Here, this is once again the same case from the same hour, but this time we're upscaling our loads by 1.6. You see in this example here, or load flow analysis, you can see that our battery is indicated in red. This means that our battery won't be able to deliver what our load is requiring. So from this, we can determine, that we will need upgrades, upgrading our battery, maybe doubling the storage of it. Yes. And as you can see, this is also the violations for that case. And once again, here we can see that overload on our battery. And once again, we can see the under voltages on the residential area.
So in this case, this is one of the cases that we used for 12 p.m. from our data, which we used it to relocate our PV system to our generation to bus 632, due to the fact that previously it was not sustaining our system, but from previous cases. But in this case, it's determined that it slightly sustain our residential area, which is reaching some nominal value of 99. Next. So this is another case where we split the PV system, our generation of 650 kilowatt generation, to the same from bus 671 and 632, which it still did not sustain our system on our residential area, which is on our left top, which we're still at 69.13% and 82.95. This is just another scenario that we use to perform analysis if our system sustain our system. Next. So this is our losses report of our system for the splitting of the PV system from 632 and 671, which we look at the kilowatts and kilovars, and it stated that our kilowatt losses are about 18.8%, and then for our kilovars is 12.5. Next.
All right, so I did a similar case of splitting it as well for the generation one of 650 kilowatts. So what I did was splitting it into two, so splitting it in half and bringing it over to the residential side onto bus one on the top left. And next. And we can see that the conditions will be under voltage in the meaning in that there's a big voltage drop in the residential area. This voltage drop can lead into many factors such as the The transformers or like the loads or just inside the residential area that's causing the under voltage. This big voltage drop is about like 10 to 20% when running it. Next.
So next we decided to perform some battery storage testing. We wanted to make sure that the initial sizing that we decided would be enough to sustain the demand during periods where the PV is not producing any energy. So we went with our initial sizing of about 600 kilowatt hours. So in order to model this, we didn't use a detailed battery model. Instead, what we used was two ideal power sources or generators in ETAP. One of them is operating on voltage control mode, which gives us the freedom to control its output. So as I mentioned, we used the projected GHI and temperature data to determine what the output would be at each hour. The other source is on swing mode. So what that means is it's going to pick up the, it's also called the slack generator sometimes. So what this does is it picks up the slack in the system, meaning if there's not enough generation to meet the demand, this generator is going to pick up the slack or provide the remaining energy required, and vice versa. If there's too much generation being provided, it's going to absorb the rest of it so that there's not too much flowing through the system. So with that being said, I'll show some of the results of our battery storage tests. Next. So as you can see here, this was the first case we decided to run as a baseline, which was 12 p.m. case. So during this case, there was relatively high PV production due to the high GHI and temperature at the time, but relatively lower demand compared to some of the other cases. So as you can see, our PV source is injecting about 600 kilowatts worth of power into the system, and our total demand is only about 327 kilowatts. So as you can see, our second source that we have acting on swing mode is actually absorbing energy, close to 300 kilowatts worth of energy. So this is essentially representing charging of our battery storage during periods of time when there's high PV production and lower demand. Next. And the opposite is true for this case. 6 p.m. is around that time where the PV production starts dropping off. Here we're really close to 0 kilowatts output from the PV system. So the battery storage is forced to provide most of that demand. As you can see, it's outputting close to 270 kilowatts now, instead of the PV producing most of the energy. So this is representing times of the day when the battery is discharging whatever it was charged with during the day to meet the demand, usually towards the evening when PV is not producing anything. Next. And similarly, here's another case where the actual output of the PV is 0. So it's completely off, and now the system is being sustained entirely by battery storage alone. So this is just a scenario to represent how the system can maintain its, maintain the demand and improve resiliency using battery storage instead of just PV alone, which, as you know, as soon as the PV stops producing, there'll be no energy to sustain the demand. So this is why it's crucial to have battery storage to pick up the demand during those off hours. Next. So here's a little table that we compiled just to show how much power is being drawn from the battery at each hour. So again, these cases were built using projected GHI and temperature data as well as projected load data. And as I mentioned, of course, there's no PV production during the later hours of the day, but still relatively higher demand from about 6 to 9 p.m. So in order to completely sustain the demand during these hours, we would suggest that we double our capacity of the battery storage to about 1,200 kilowatt hours. And that would give us a resiliency of about 6 hours, which is more than what we had initially hoped for. We could get by on about 3 hours during this peak time with 0 PV production. Obviously, we would get more resiliency, during earlier hours of the day when the PV is still producing and we have a bit lower demand. But this just goes to show that even as a worst case scenario, Even with our 600 kilowatt hour capacity that we initially chose, we'd be able to sustain the system, for about roughly 3 hours with no PV production at all. Of course, if we wanted to increase that to get the whole rest of the day without any PV production, we could probably upgrade the capacity, double it in order to give us a resiliency of 6 hours, which is greater than our initial goal. Next.
Overall, it has been hard on all of us, especially everybody else from this COVID, no in-person contact, etc. We originally wanted to use Simulink with our original 13 bus test feeder, but we ran into some software issues where load flow analysis and other parts was not entirely our fault, but the program lacked some features that caused us to go to ETAP for this direction. We ran into other situations on how to use these new programs in smaller amount of time that we had and changing how we want to approach this project. In the end, we wanted to finish this project strong, the school year strong, and be proud of what we have accomplished. We were able to determine 650 kilowatts PV source and battery storage that can stand a capacity of 1200 kilowatts per hour for about 6 hours. We wanted to say thank you for listening in and have a wonderful day.